So now we have the panel session. So unfortunately, Max couldn't attend the panel because he's giving another talk in another session. But are there any questions from the audience for the panel members to initiate the discussion? Yes.
Maybe a really specific question for Tobias, but I've talked about with John a few times about how in Alive 2 they have lots of these bit vector, exactly as you say, problems, and they want to kind of formally prove them, but they only look at like specific bit vector 16, 12, 14, right? And we always want to be, can we prove them for all bit vectors? Do you think your lean interface will provide us a mechanism to say, not just for all xy of type bit vector 1, but of type bit vector n?
Yes, I'm convinced our lean already supports to quantify over the bit width in the statements. The moment you quantify over the bit width in your statement, I mean, it's a hard proof. It becomes hard. There's no decision procedure to solve that for you, right? So what we are working with the lean community, actually, they're heavily, the lean FO is now heavily investing in the like bit vector level decision procedures. So lean will have actually quite high performance automation for bit vector level reasoning up to a fixed bit width. And then there's just a large math library with a couple of like decision procedures for subsets of bit vector theories that can handle the arbitrary rates. And what actually is quite interesting, so we looked at a couple of proofs, and if you want to prove like theorems over arbitrary bit width that are not trivial, sometimes you find this interesting pattern that if you need to case analyze in your proof, and several of these cases are actually then very quickly becoming fixed bit width. So you have this interesting case where then a subset of your proof can just be dispatched to your automatic decision procedure for fixed bit width, and then you just pretty much need to cover the general case either by yourself or using Omega or whatever.
So for the second and last talk, so specifically related to control flow, I'm curious how you would handle propagating traits across complex control flow structures, and specifically also interprocedure analysis. So for the second talk, it's about how do you detect patterns if it's scattered across multiple different functions. And for the last talk, so it's 8, 9 different shapes and properties, how do you propagate the knowledge that a certain intermediate has those shapes through complex control flow, and do you make actually already use of it?
I think in my case, the answer is simple. We don't propagate it. You have to say what kind of structure you would like to use to store each intermediate. I think part of the reason it's hard to propagate is that you don't know how the runtime values might interact to produce something which has structure or to produce something which doesn't. One challenge that I found when trying to wrap this up in a higher level API is that you sort of ask a really simple question, like which format should I use for the transpose of a sparse matrix? And it's like, I don't actually know in certain cases whether it makes sense to store the bottom level sparse or the bottom level dense or the top level, because it does actually depend on how those non-zeros interact and how they're clustered together. So we can make safe decisions. Yeah.
For the question about interprocedural analysis, basically right now we don't support jumping into some user functions unless it's been inlined. So the easy hack is just to make sure it's inlined, and then that's fine. But in terms of looking for formats specifically, most of the time they are specified by some include some header somewhere which will be already pulled in. So vast majority of the time when you're looking at the LLVM IR level, you don't need to do anything extra to have full knowledge of the data structures that you're accessing. But it does quickly become complicated when you have multiple storage formats in the same kernel, especially if you are writing to a sparse storage as output, And the way that we handle that right now is we have like a greedy work list kind of algorithm to start with the what looks like the leaves of pointers in that graph that I showed, and every time we detect one, to kind of pop it off the work list until we reach a fixed point. And that works for all of the benchmarks right now, but it's not really a solution that can handle all possible cases because it's just too complicated. Yeah.
So I have a couple questions that are very specific, so maybe we can take it offline later. But one question I had for Avery, which is like the work that I presented on in an earlier session, Mosaic, is very similar to spec, but instead of a bottom-up fashion, it's top-down, and instead of LLVM-IR, it's within like tensor index notation. So my question is basically, when we did this, we had this verified mechanism for the schedules and for deducting patterns, but oftentimes your function call backend needs arguments that your code doesn't necessarily provide. So for example, in a CSR matrix, you're not guaranteed to have the dense dimension anywhere because you don't actually need it in the loop nest calculation. So then how do you actually end up emitting the backend code properly? Because it seems like a final step, and that step seems to not be verified.
Yeah, good question. There are two scenarios. So first scenario is a lot of the time user code omits very common parameters like alpha and beta. And so the way we handle that is we have some kind of weird rewrite rules where we like inject back in facts. So like if you have, A, like AI, you're accessing, matrix A at position I, that's equivalent to AI times 1. And, you can always put in any free variable name as long as you multiply it by 0. So we actually we do a few rounds of those rules where we like inject back in that kind of information so that we can detect those really common values of alpha and beta. So like in the example I showed, there was no alpha and beta specified. We just extract them through the quality saturation process. For the second part of the question, which was about for example with CSR extracting back out one of the missing dimensions, that's folded into the precondition check, because in the precondition check we're iterating over the row pointer and the call pointer, again for this CSR example, and so you can imagine the case where you just look to see how many columns there are in the sparse matrix, and any extra columns would have just been all zeros. So it doesn't really matter about those anyway. It doesn't change the semantics to just find the max number of columns and say that is your dimension. Yeah.
Question for you, which is kind of connected to the presentation that Max had. So Max basically said that for the equality saturation technique, basically in principle what it does is that it allows you to do a search over basically the space of semantically equivalent programs. And then he said that, okay, there was a combination of that with this data log ideas, and they introduced egglog. You said that you have used egglog. What is it with egglog that you have used that you couldn't use just pure egg?
So I started off with egg, and then there was something I needed, and I can't remember what it is. I think with the current version of how things work, I think I could make it work with egg, but the main reason I switched is because egglog is a lot faster and has a bit more of like a fluent Python API. It seemed to be the way things were going from their research, and it was the only one that was like most actively maintained. So egg was like no longer actively maintained, egglog was. So I thought, okay, this is a better choice.
Okay.
Yeah.
Yes.
So this is the compiler framework session, so I'll ask a question about frameworks. In research, you have this choice. You can hack up prototypes and you can explore ideas really quick, but you do it at a low level of resolution. Or you can build big frameworks, and the benefit of that is that you can have a lot of impact that way, and maybe you can explore ideas in more resolution, but then you go slower, so you can't explore as many ideas. What's your thoughts on these options?
I'll let someone else go first this time.
You can go.
Can you repeat your question again?
Oh, maybe it wasn't. So you can, when you do research, especially in academia, but also in industry labs, you get this choice. You can hack up prototypes and explore your ideas to a low level of resolution, and you can move really quick, so you can explore many ideas, and you can go quicker that way. Or you can build big frameworks. Maybe you can open source them. Maybe you can make them a little bit more industry strength. You get to explore your ideas to high levels of resolution, but maybe you can't explore as many ideas because you spend more time coding. So what's your thoughts on the trade-off?
So maybe I would actually slightly rephrase that, right? So it depends a little bit, like if there are pre-existing large frameworks available, right? I think it's definitely like if you work with large frameworks, there's a like learning curve. You need to get up to speed with that framework that takes quite a while. I would actually challenge the statement that if you work in a large framework and that this somehow slows down your research, but it's a very specific skill set to develop, right? If you try to solve like any of the frameworks presented here, I mean, if you hack them up quickly to get a quick result, I mean, I think you will be heavily burned, and it's just it doesn't work. You can't hack up complicated research in many cases quickly. And I think so sometimes it really pays off in kind of learning the skills to navigate a large ecosystem and use the appropriate tools well. It takes a lot of time to or like at least take some training to learn these skills. But afterwards, I think you actually kind of almost become a wizard in combining like highly complicated systems in very novel ways, which I believe actually can be sometimes quite fast. Obviously, like some of the research I present actually builds up a lot of tools itself, which I guess can't be necessarily fast, but that is a very deliberate strategic decision to kind of, for example, connecting MLI and Lean. I mean, that's a lot of like, we did a lot of non-research bit vector stuff, which really is not research, but it connects ecosystem where I think in a couple of months, we'll see again this kind of catalyst of high performance research or quick research if the framework is built sensibly. Not sure.
I love rewriting systems. I think that everybody should rewrite systems all the time and frequently. But I like there. I feel like
nice. Don't give someone an also.
No, I mean I really like I'm stubborn, and there's a lot of things that I would not have learned if I didn't rewrite systems, and that I appreciate more now that I have, and that. You know, it may be that there are like certain ways and results are presented that kind of gloss over some interesting thing that you wouldn't have known if you didn't like build it up. It also, like when you work in an established system, it constrains you to the decisions that were made at that time, right? And so you can't, you know, you're locked into certain, you know, assumptions and like things that are built into the system, and you can't get around them. So I think that's like the challenge. I will say though that like trying to productionize systems or working in larger frameworks also like, of course, leads to new questions, right? I would not have asked myself how to transpose a sparse tensor and then pick the format of the output unless somebody was saying, oh, you really have to, you know, make this new interface for it or something like that, right? So that the users will be happy, or so that, you know, it'll integrate with this existing framework or something like that. So.
But the thing is, when the framework collect lot of capabilities, it gets harder and harder to do this rewrite part in there, because you at the beginning of research, expectations are very low. You get some very simple thing working and you're very happy, you can publish a paper, and as time progresses, you have to build much more thing, and at that time it gets harder and harder to do that. So, but the thing about research is you don't know what you're doing when you start, so you will always end up with some new thing that you somehow or other kind of fit into the like put a square peg through a round hole, and when you do few of those, your framework is pretty much dead.
I like to think that we will rewrite these things over and over again until they're perfect, but I don't I don't know if that's true.
And just to clarify, you were not referring to rewrite systems. Term rewrite
Those are great
systems.
too.
Yeah.
Can we just automate that process?
Yeah. So do you have any comments on that?
Yeah, I agree with everything that's been said. Personally, I don't have the skill of being able to anticipate every possible thing and plan everything out and then execute it perfectly. I know a few, like 1 or 2 people who can do that, and I wish that I could, but I just can't. So for me, the only solution is to very quickly experiment with a bunch of different things and then decide the path forward and go backwards, and maybe do that several times. And I do think there are also benefits to that approach, even though on the surface it may seem like you're wasting time. Like I think a really good example of this is the CVC solver. They, every couple of years rewrite the entire solver bottom up, because they just decide, okay, we learned lessons from the last time we did it, and let's just start fresh, let's start all over again. And every single time they do that, they always beat what they did last time. So I think, it can be really beneficial.
Yeah. So if there are no more questions, I want to ask actually one question, which you can combine also with the closing statements. If you were to rebuild the system that you built, how would you have done it differently this time?
I'm re-implementing it in MLIR, which I should have done from the beginning. Because what I didn't show here, but you can watch. I did a talk at the egress workshop yesterday that you can look on YouTube, and I explained it in detail. But basically, translating the LLVM IR into an egraph term is not straightforward, especially because of how memory is modeled in LLVM. And so it takes a lot of effort. It's not the LLVM infrastructure itself is not really designed to handle that. So I should have written it as a dialect in MLIR. It would have been much easier, and that's what I'm doing now. Yeah.
And just to clarify, you mean that using the dialect of MLIR, you don't necessarily mean that
creating a new dialect in
Yeah.
MLIR that has a one-to-one translation to an egraph term.
Okay. Thanks. Tobias?
Yeah, I'm not sure actually. I'm quite happy with the projects we have. I mean, our lean MLIR stuff I think is took way longer than I thought. I mean, I need to learn more about interactive theorem proofers and more of the theory. And in particular, I think what in general for some of the projects I think is really important is to get the kind of like the team right. It's you need expertise from many different areas to get really like many design decisions right, and it's just like an endless lesson that I keep relearning and relearning. There's so much knowledge in our community, and typically like a year after you develop your framework, you talk with the person and said, yeah, they knew what I should have done.
I've been thinking a lot about what I would put in a rewrite of my system, but I think the main thing is that, like you were saying, rewriting is good. It's almost purely syntactic. I think that leaning into that would have made things a little simpler.
Okay. And let's thank the panel members again.